Doppler shift, or Doppler effect, is when you observe a frequency that is different than the frequency that the source is making, because you, the observer, and the source of the waves are moving relative to each other. Let's see what we mean. This is the race car sound, where you have a change in pitch. Here we go. You could hear that drop in frequency as it went by you, because in the beginning it's coming toward you, and afterwards it's going away from you. Sirens are really great for this, because not only is there a change in pitch, but there's a change in frequency of the beat from ba 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 to ba 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 ba. Listen for this. So we want to know about Doppler shifting. We can go look at Wikipedia. Got all the information. It shows the shift in wavelength because of the motion of the source. We see them lambda smaller in front than in back. Give an example of a swan on a lake. And so here we go. We have a source of waves. It could be light waves or sound waves moving off in all directions at equal speeds. But when the source is moving, the wavelength is much larger behind than it is in front. You can think of the waves as getting crunched up in front and spread out behind. We also see that if the source is moving at the same speed as the speed of the wave or the speed of sound, we have a bunching up in front of the source, providing a sonic boom. If the source of the waves is moving faster than the speed of the waves, we get a shock wave right here. And the angle that the shock wave makes is a function of how much faster than the speed of sound the source is moving. And then we have all kinds of other interesting things, astronomy, red shifting, that we can read about if we like. Okay, so we can see here is the effect made by the source moving. And why do we get these circles that are bunched up on one side and spread out on the other? Well, that's because this wave, it was made when the source was back here and the waves moved out in all directions. But this circle was made somewhat later when the source was here. And now the source is here. So as the source moves along, it continues to make waves that travel with equal speed out in all directions. We also know that there can be an effect due to my motion. For instance, if I'm moving into the waves, I know I hit them faster, boom, 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 than if I'm moving along with them. If you move into the waves, you will pass them quicker, and you will perceive a higher frequency. And if you're moving with the waves, the frequency will be perceived as less. In fact, a surfer will tell you, if you match the speed of the wave, the frequency will go to 0. No waves will go under you. So how do we calculate this change in frequency? So if I know the frequency that the source is making, how do I calculate what frequency I observe? So Wikipedia will give us this nifty formula. And it's very confusing because there's a speed of sound, there's a speed of the source, there's a speed of the observer, and there's plus or minus depending which way you're going. And I can tell you this is very confusing and I can't use it. And if you are able to memorize it, you will likely get the wrong answer. Regardless, you will get no credit on any test of mine, because this is not about understanding. I have a much better formula for you. It's this one. Velocity is distance over time. The velocity of the wave is how far it goes divided by the amount of time it takes, or the wavelength divided by the period, or lambda times frequency. And so this allows us to calculate the wavelength. Lambda is the speed of the wave as it moves away from the source divided by the frequency that the source is making the waves. But the thing is, this speed, how fast they move away from the source, is a function of how fast the wave is moving and how fast the source is moving. So you can see, if you're in a boat, for instance, you can see the waves move forward away from you much slower than the waves move backward away from you, because you are moving through the medium. So here, the relative speed of the wave moving away from you is, if this is sound, is the speed of sound plus how fast you're going the other direction. The speed of the waves in front of you are going to be the speed of sound minus how fast you are moving toward them. So here, this is why you get a much larger wavelength behind than you do in front. So of course, if you're standing here, you're going to perceive a much lower frequency because the wavelength is larger than you would if you were here. You perceive a much higher frequency at the shorter wavelength. But of course, that's not the only story, because you can move into the waves, pushing the speed at which the waves hit you upward. Or you could move with the waves, pushing the speed that the waves hit you downward and lowering the frequency. So here, the speed is how fast the wave moves into the observer. Again, if you're moving toward the source, you're going to have to add your speeds. It's the speed of the wave plus your speed. And if you move away from the source, it's going to be the speed of the waves minus your speed. And again, the surfer will tell you that the frequency of the waves hitting me is 0 because I'm moving at the same speed of the wave. So you'd subtract those off and you get an observed frequency of 0. Yes, if we go at the same speed of the wave, you will build up a pressure wave where they all add right here, and you'll have a huge sonic boom. You can actually see it sometimes. If the conditions are just right, you'll get a condensation of the humidity in the air. And so we can try to see this. Let's take a look. Now you heard the sonic boom and you saw it. Now this is a supersonic. Here the wave has only gone this far since the source was here making it, but the source has moved further. And so we could see this represents a speed of about Mach 1.5. Mach meaning it's going about 1.5 times the speed of sound. Because again, the wave has gone this far, but the source has gone about 50% further. And so we can look at a number of examples where here is the shadow of a model in a wind tunnel. So we can see that from any given point, the shock wave has moved some distance x. The jet itself has moved about 2.5 times as far, indicating a speed of about 2.5 times the speed of sound. Now, I'm off by a little bit, and so there must be some error in exactly how I viewed what is the shock wave. Potentially, this shock wave comes up to here. Here's another really nice one. We presume that the bullet and the shock wave of the sound both came at the same time from the nozzle. And you can see, right, the bullet has gone about 50% further than the shock wave. Or from any given point, we can see that the bullet has moved about 1.5 times as far as the shock wave has moved at the speed of sound. So again, this bullet is probably going about 1.5 times the speed of sound. So there you go. That's your Doppler shift. And I challenge you to go and tell me, why do they call it red shift or blue shift? Your astronomers will help you with that. Thanks.